So we want to talk about the off-grid PV power systems. This is a brief idea of what the components look like. We already talked about this, but I'm just going to refresh our memory before we go into the design of an off-grid power systems, because we are going to have to try to design each of these components and see exactly, how the design works. First of all, we have a PV array, okay? Depending on the size of your power system, the PV array size would vary, okay? And we do know that the PV array is made up of PV modules, and the modules are made up of PV solar cells, okay? So, and they are the most important components when it comes to collecting energy from the sun and converting the energy of the sun to electrical energy. Then for an off-grid power system, we also have a section here called the controller, the charge controller, and the battery bank. You already know what a battery bank is used for. So we're going to try to design the battery bank today too. We're going to try to design the charge controller too. And I'm going to tell you exactly how to design each of those components. Then we're going to talk about the inverter, which is going to be the off-grid inverter or standalone inverter. That is what is used for standalone PV systems. Then we have our distribution panel. And then before the inverter converts the DC electrical energy to AC electrical energy, if we have DC load, we can easily connect our DC load to the output energy before the inverter converts the DC electrical energy to AC energy. And then when the conversion has taken place, it goes through the distribution panel. The AC energy goes through the distribution panel, and then it goes to supply our AC electrical load. The battery bank here stores energy so that whenever there is no sun or whenever we have excess demand, excess load demand, we can draw more power from the battery power bank. And then we have the charge controller that ensures that the connections in the electrical circuit are respected and there are no mismatches. The battery bank is not overdrawn and it is not overcharged. So the charge controller would also manage that situation. All right, so you notice that this is our balance of system. All in all, the balance of system is going to be here. The entire section here is called the balance of system, as you can see. Okay, so, and then you can see we have this section called the loads. We have the AC loads, and then we have the DC loads. So let's talk about the battery characteristics, the kind of batteries that we use for the PV power systems. First of all, there are some terms about the battery that we should be familiar with. One of those terms is the rated voltage. The rated voltage is the nominal voltage at which the battery is supposed to operate. Okay, it could be 12 volt, it could be 24 volt, it could be 48 volt, depending on the size and capacity of the battery. Talking about capacity, when we say capacity, what are we talking about? It means the amount of charge that the battery can deliver at a particular rated voltage or at the rated voltage of the battery. Okay, so the unit of rated voltage, of course, is our volt, as you know, and the unit of capacity is going to be ampere hours or milliampere hours. That is what we use to represent the unit of the battery capacity. Okay. Current is usually given as charge over time. You know this from your basic physics. Current is equal to charge over time. And then from what you can see here, if you have 1 ampere hour as the charge, okay, that means it will be the same thing as 1 coulomb per second hours, because ampere is actually the same thing as coulomb per second, all right? Ampere is the same thing as coulombs per second, all right? So if you have 1 ampere hour, you could write it as 1 coulombs per second hour. And then if you convert 1 hour to seconds, it will give you 3,600 seconds, because 1 hour is equal to 60 minutes. So if you convert 1 hour to seconds, you have 3,600 seconds. That cancels these seconds here, and you are going to be left with 3,600 coulombs. Okay, so this is just a simple analysis to give you an idea of how to play with the capacity and the ratings of a battery. Okay. Okay, so when we talk about batteries and then we mention the term voltage, what comes to your mind? The first thing you should know is that the voltage is chemistry based. Then we have the capacity. Capacity is based on the quantity of active energy that is being used. The quantity of active energy that is being used, all right? Then we have energy capacity. So you should be able to differentiate between energy capacity and the capacity of the battery. The energy capacity is the total amount of energy that the device can store. Look at these two properly. You should be able to, say the difference between them. Okay, capacity is based on the quantity of active materials used. That's okay, we know that. Capacity is the amount of charge that the battery can deliver at the rated voltage. Energy capacity is the total amount of energy that the device can store. And the unit of energy capacity is given as watt hours and then kilowatt hours if you're dealing with very large systems. So the energy capacity of a battery is usually equal to the capacity of the battery multiplied by the voltage of the battery. So you can see the difference right now. So as you can see here, you can see the voltage is going to be between the two terminals. Okay, we have the cathode and the anode, are the terms used to describe the two ends of the battery, the cathode and the anode. One of them is positive and the other is negative. And then when, for example, if you look at this battery, it has 10 ampere hours capacity. What this simply means is that in 10 hours, this battery can be charged by 1 ampere in 10 hours. That is what it simply means. When you have 10 ampere hours. Let me just clean this up a little bit and then we can move on. So let's try to play with some calculations. As we discussed, stored energy is measured in ampere hours. Please don't forget about that. Stored energy is measured in ampere hours. There is something we also refer to as the E rate of the battery. I'm going to talk about that as we move on. So let's pay attention. First of all, charging and discharging of a battery depends on the direction of current into and from the battery, respectively. Okay, so we have a term referred to as a C rate. It is a measure of the rate of discharge of the battery relative to its capacity. And it is usually given as 1 divided by battery capacity divided by 1 hour. This is an important definition you have to pay attention to. 1 C rate means discharge current will discharge entire battery in 1 hour. So when you're given 1 C rate, okay, when you have 1 C rate, it simply means that discharge current will discharge entire battery in 1 hour. For a battery with a capacity of 100 ampere hours, this means discharge current of 100 amperes. I'm going to explain this to you in details as we go on. Now that you know what the C rate means, which is a measure of the rate of discharge of the battery relative to its capacity, and it is given as 1 over battery capacity divided by 1 hour. We have I, this is I, current, equal to, for example, this is I right at the top here, C rate equal to current I over, battery capacity over 1 hour. If you cross multiply, this will mean that your I is equal to C rate multiplied by battery capacity divided by 1 hour. Okay, so you see that I equal to C rate multiplied by the battery capacity divided by 1 hour. All right, so in the case where we have just 1 C rate, like I explained earlier, that would mean you have 1, you replace the C rate here with 1, all right? And then let's say we have a 10 ampere hours battery. So that's the battery capacity, you put 10 ampere hours here, divided by 1 hour. This H will cancel this H, and what you would have left is going to be 10 amperes, all right? So it simply means for 1 C rate, your current will be equal to 10 amperes. All right, and the battery will be discharged. These 10 amperes will be discharged in 1 hour. That's what it simply means. 10 amperes will be discharged in 1 hour. When we have 1 C rate and the capacity is 10 ampere hours, 10 amperes will be discharged in 1 hour. Now, what happens if we have 2 C rate? It simply means we have I equal to C rate multiplied by battery capacity divided by 1 hour. You replace this C rate with 2 because we have 2 C rate. If the charge remains 10 ampere hours divided by 1 hour, this H also cancels this H, and what you have left will be 2 times 10, and that is 20 amperes. All right. So what can you see here? It simply means that for 2 C rate, the amount of current discharged in 1 hour is going to be 20 amperes. You see that? All right. The amount discharged in 1 hour is going to be 20 amperes. All right. So for 2C rate, what you would notice here is that the total amount of time you would need would be equal to C over 2, 1 over 2, and that will give us 0.5 hours. Okay, so for 2 Cs, you will need 0.5 hours to discharge the battery. For 2 Cs, you will need 0.5 hours to discharge the battery. And then when the C rate is 0.5, what would happen? You would find out that the discharge current is actually 5 amperes now. All right, so this will take more time. You will need 2 hours to discharge these, okay, when you have a C rate of 0.5. How do you find the time that it will take to discharge the amount of current for the respective C rate? You use this formula. T is equal to battery capacity divided by battery capacity multiplied by the C rate, and that gives you 1 over N. It gives you 1 over N. All right, where N will represent the value given to the C rate. So when the C rate is 2, the time required to discharge that battery capacity, the current in that battery will be 1 over 2, and this will give you 0.5. That is why we have 0.5 here. When the C rate is 5, all right, how do you know the time that you would need to discharge the amount of current in that battery? You will need 1 over 5, and that would give you 0.2 hours is what you would need to discharge the amount of current in that particular battery. And by the way, if they ask you to find the amount of current that can be discharged, let's say we are dealing with 10 ampere hours of the capacity of the battery, and they ask you to find the amount of current that can be discharged in these 0.2 hours, what would happen? You just use this exact formula we have here. So you can see that your I would now be equal to, the C rate is 5. So you can see we have 5 multiplied by the capacity. Okay, we are assuming the capacity is still 10 ampere hours divided by 1 hour. So this hour cancels this hour, and then you find out that you have 50 amperes left. Okay, so that simply means that this 50 amperes will be discharged in 0.2 hours. Okay, that is the amount of time you will need to discharge this 50 amperes available to be discharged in the battery. All right, so it's important that you understand how to play with these, so that you get a very deep understanding. All right, I just want to quickly mention this in passing so that you can pay attention to it. When we are profiling batteries for PV power systems, you can be told that you have a C over 20 profile for your battery. You can be told that you have a C over 10 profile for your battery. You can be told that you have a C over 2 profile for your battery. Okay, you can be told that you have a 2C profile, a 3C profile for your battery. When you hear the term 2C profile, it means you have the C rate is 2. When you hear the term C over 10 profile, it means that you can assume like a 1 over 10 C rate. When we say we have a C over 20 profile for our battery, this simply means that constant current can be extracted for 20 hours. That's what it simply means. For example, if you have an 80, let's say you have a battery capacity of 80 ampere hours, okay, in this particular case, if the capacity is 80 ampere hours, all right, this simply means that you can actually remove, how much current can you remove from this battery? All right, if the profile of the battery is C over 20 and the capacity of the battery is 80 amperes, this would mean that you can actually remove 80. This implies that you can remove 80 ampere hours divided by 20 hours. These hours will cancel hours, and then you are left with 20 here, 1, 20 here, 4. So this will give you 4 hours, 4 amperes. So it simply means that 4 amperes can be discharged in 20 hours. That's what it simply means. 4 amperes can be discharged in 20 hours. Also, if you have a C over 10 profiling, if you have a C over 10 battery profile, it simply means that if the energy is, let's say the energy is 100 ampere hours, or the energy is still this 80 ampere hours, this implies that you have 80 ampere hours over 10 hours. Okay, it means that constant current can be removed from the battery in 10 hours. That's what it simply means. That's what this profiling means. So this H cancels this H, and then you are left with 8 amperes. So how much current can be removed? You can remove 8 amperes in 10 hours if the profile of your battery is C/10. All right. So very briefly, let's talk about the round trip efficiency. What is the round trip efficiency? The round trip efficiency, you can abbreviate it as RTE. Okay, the round trip efficiency is the ratio of the energy stored on the battery to energy you take from the battery or energy retrieved from the battery, which is also referred to as the AC to AC efficiency. So what you can see here is 10 kilowatt is going into the battery, and then what is going out of the battery is 8 kilowatt hour. The efficiency in this place would be output energy divided by the input energy. In this case, it's just going to be 8 kilowatt hour divided by 10 kilowatt hour, and that will be multiplied by 100, and that would give us 80%. Okay, so we're going to talk about the depth of discharge and then the state of charge. All right, the state of charge is the percentage of the battery capacity available for discharge. So it is usually energy available divided by battery capacity multiplied by the voltage, all right, of the battery multiplied by 100, and you get your value in percentage. So this gives you your state of charge. And then the depth of discharge is the percentage of the battery capacity that has been discharged. So that would be energy discharged divided by capacity of the battery multiplied by its voltage, everything multiplied by 100 will give you depth of discharge. This is DOD, by the way. So change this to DOD in your notes. This is depth of discharge. So this is depth of discharge. It will be equal to E discharge divided by battery capacity multiplied by voltage, everything multiplied by 100. It is also given in percentage. That's why we are multiplying by 100 and 100 here. So if we have a 10 ampere hour battery and then we use 2 ampere hours out of the 10 ampere hours battery, according to our definition, the percentage of the battery capacity available for discharge would be 10 minus 2, and that would be equal to 8. So you would have 8 over the capacity, which is 10, times 100. That gives us this 80%. Depth of discharge is the percentage of the battery capacity that has been discharged. So if we have 10 amperes and we have used 2, it means 2 has been discharged. So depth of discharge will be 2 all divided by 10 multiplied by 100 will give us our depth of discharge, and then you can see you have a 20% here. All right, now we're going to quickly talk about the cycle life of a battery. Cycle lifetime is defined as the number of charging and discharging cycles after which the battery capacity drops below 80% of the nominal value. The nominal value is actually the nameplate value. It is the manufacturer's value, okay? The value of the battery at the point of purchase, the value recommended and given by the manufacturer is the nominal value. So lifetime is defined, or cycle lifetime is defined as the number of charging and discharging cycles after which the battery capacity drops below that nominal value. That's what we refer to as the cycle lifetime of a battery. So life cycle depends on depth of discharge and the temperature. The battery will last longer if the average depth of discharge could be reduced over its normal operation. So like we said, depth of discharge is the percentage of the battery capacity that has been discharged. In other words, the battery will last longer. The battery will last longer if the average DOD, depth of discharge, could be reduced over its normal operation. The higher the average depth of discharge, the shorter the life of the battery. The higher the depth of discharge, the shorter the cycle lifetime of the battery. So our aim, if you want to actually make a battery last longer, you make sure that the depth of discharge, over its normal operation is reduced. It's not too high. The higher it is, the lower the the cycle lifetime of the battery. Okay, so please pay attention to that. So there's a graph here that talks about the cycle numbers. When they say cycle number, they're talking about charging and discharging. Okay, so a battery is fully charged right now. You use it and discharge it to a particular point, and then you charge it back. That is one cycle. Then you use it again to a particular level, you charge it back. That is another cycle. If you charge and discharge, charge and discharge, charge and discharge, those are what we refer to as cycles. So that could happen once a day, twice a day, 3 times a day, 4 cycles, 5 cycles, 20 cycles as we move on, depending on what you're doing and what you're using your battery for, and the design of the battery and the system. All right. That is why we have said at the beginning that the cycle lifetime is defined as a number of charging and discharging cycles that we can have, after which the battery capacity drops below 80%. So your 100% battery capacity can actually drop, the performance can actually drop below 80%, such that you can no longer charge it to 100% anymore. You can only charge it to 80%. It is possible. That way we can say that, the battery, the efficiency of the battery is dropping, and then, the capacity is not as high as it used to be. So we have the cycle numbers, as you can see here. It could be 8,000 cycles, 6,000 cycles, that is 8,000 charging and discharging times, 6,000 charging and discharging times. And then you can see here we have the depth of discharge. So you will find out that as the depth of discharge increases, the number of cycles decreases. And then you would notice that these are actually temperatures too. Okay, these are temperatures, because the life cycle also depends on temperature, not only on the depth of discharge. It also depends on the temperature. So when the temperature is high, what would you notice? For PV systems, we had said that when temperature is high, the performance of the PV drops. When temperature is high and then the solar radiation is constant, the performance of the PV drops. So we don't want the temperature to be excessively high, because it's going to damage or reduce the output of the system. All right. But then the opposite is the case for the battery. The higher the temperature in the case of battery, the more the performance of the battery, the better the battery performs. In the case of the battery, the higher the temperature, the better the battery performs. Okay. So pay attention to that. Let's take it a step further. So battery capacity versus temperature. The higher the temperature, the higher the battery capacity. This is because at high temperatures, the chemicals in the battery are more active, and therefore the chemical activity tends to increase the battery capacity. You can see that now. So the higher the temperature, the more the capacity of the battery, the more the performance of the particular battery. So let's quickly talk about a charge controller now. Charge controller is used with batteries, therefore they are only in standalone systems. You can only find charge controller in standalone systems because they are actually used with batteries. And there are different types of charge controllers, and then they have to be selected based on the capacity of the battery, based on the operating voltages. I'm going to show you how to do the design, and then you know which one you actually select for your system. All right. Now, what are the battery operational requirements that are available that should be given attention? Okay, what you see here, you can see that we have, this is a sun, and then this is the module. Okay, this is the module. So as the sun hits the module, you can see that we have a load here. Energy is produced, which is the DC energy produced from here. Okay, and then the DC energy that is produced, goes to the battery, all right, and it is stored on the battery, and then it can also go to the load so that the load can actually use it. Important points that you want to pay attention to here is the voltage, the current, the state of charge, the depth of discharge, the cycle life of a battery. These are important points you want to pay attention to. PV array responds dynamically to ambient conditions like irradiance temperature, and other factors like shading and other ambient conditions that you can think of. So PV responds, dynamically to all of those, all those ambient conditions. Battery technologies have strict voltage and current limits required for their optimal functioning. Lead acid battery responds poorly to overcharge and over discharge. So that means when you overcharge your battery, or when you overdraw energy from your battery, or you over discharge your battery, for a lead acid battery, they respond poorly to that. Under such circumstances, a direct coupling between a PV array, battery, and load is far from healthy for the battery. Okay, so that is why we don't have direct coupling of, one of the reasons we don't have direct coupling of, PV array with the battery, or probably battery with the load. Okay, there has to be a charge controller. All right, so one of the main responsibilities of the charge controller is just to make sure that that the circuit requirements are actually respected. This is very important. How do we prevent over discharging and overcharging? When the sun is shining in the peak summer, there is enough PV energy meeting the load. So the excess energy is sent to the battery. So as the energy is produced, it is sent to the battery. But when the battery is fully charged, what happens? This is where the problem comes. When the battery is fully charged and the PV array is still connected to the battery and continues to charge the battery tends to overcharge. We don't want that to happen. Otherwise, your battery is going to get damaged sooner than later. So the problems with that is that there will be gas formation in the battery. You will lose capacity, and it might also lead to overheating. And these are situations that you don't want to put your battery in. That is the case for overcharging. Also for over discharging, it is possible that in severe winters when we don't have enough irradiance, we don't have enough sun to power the PV, or probably cases where we have excessive demand, by the load. The load demand could be more than the supply power from the PV or from the battery. Okay, so the battery becomes heavily drawn because we need more power to supply the load. So when the battery becomes heavily drawn, it simply means we are taking all the power that we have installed, that we have saved in the battery. Okay, and for all batteries, there is a minimum level you do not draw them beyond. All right, so what you find out is that if care is not taken during the winters or during times when we have severe heavy load demand, the battery is heavily drawn. The battery under such conditions tends to be over discharged. When that happens, it shortens the life of the battery. So we do not want over discharging to happen to our battery. We do not want overcharging to also happen to our battery. These are two important points that we have to pay attention to. So when we have a charge controller, the charge controller ensures that we prevent overcharging, that the battery, as soon as the battery is fully charged, it is sensed by the charge controller, and the charge controller ensures that no more energy is stored in that particular battery. Also, when you have a charge controller and then you are drawing energy from the battery, once the battery reaches its depth of discharge, the charge controller senses it, because they communicate. It's going to be a sensor that communicates, and then the charge controller disconnects the battery from being drawn from, it disconnects the battery from the load, so the load cannot draw energy in again from the battery at that particular point. So that way, the charge controller is protecting the battery. It is ensuring that the requirement of the battery is being met, is being respected, is not violated. All right. That way, you are protecting the system. Also, there are several other reasons we need the charge controller. Sometimes we don't want the energy in our battery to go back to our previous system, because it has to be we want it to just be a one-way movement. So we don't want energy from the battery to go to the PV system. The charge controller also works and ensures that we have a one-direction movement of energy, into the battery. So now let's quickly talk about the design of an off-grid PV power system. An off-grid PV power system is the same thing as standalone PV power system, like we mentioned. So when you want to design one, this is like a flow chart that you have to pay attention to. This is a very important chart that can help your understanding and then help you not to miss any important detail. You will see that what you have here as base is PV array, and then the PV array is fed from 3 points. We have the equivalent sun hours being fed to the PV array. We have load demand being fed to the PV array, and then we have accounting for losses being fed into this place. What I mean by something being fed into the PV array design is that we have to pay attention to the losses All right, so we have to account for losses, we have to account for load demand, and we have to account for sun hours to have a proper design for our PV array. Otherwise, we might design a PV array that may not be able to accommodate the kind of load we have. So we must know the load we have. We must understand the load we have before we can design a proper PV array. We must understand the kind of losses that we are likely to have and factor in those losses while designing our PV array, so that at the end of the day, when those losses have occurred, we would still have an output that can meet our load demand. And then we must factor in our sun hours. Majorly, PV array thrives in locations where we have high solar radiation. So if the irradiance is low, it simply means that we cannot get as much as we need from our PV array. So we have to factor in the fact that there has to be enough sun hours. If we don't have enough sun hours, whatever sun hours we have to be able to design our PV array in such a way that the amount of energy we can get from the PV array will be commensurate with the load, or we will adjust the load in such a way that the kind of load that can actually use that energy that is connected to the PV array. This is very important. Otherwise, if we overload the PV array, we might end up having some kind of mismatch between the energy demand and energy supply. This is very, very important. So we take into account these three things when designing our PV. All right. Then from the design of the PV, we can then go ahead and design our charge controller. We can go ahead and design our battery. When designing our battery, we have to take into account the days of autonomy. When we say days of autonomy, what does it mean? For how long do you want to use your battery without charging it? There are some batteries that you can use for 2 days, and then they can supply a load for 2 days without even charging them at all. For 2 days. There are some batteries that you can use for 3 days. The days of autonomy is 3. There are some batteries that the days of autonomy could be 5. Some days of autonomy could be 6. So the higher the days of autonomy, the more expensive your battery design would be. The more complex the battery design would be, the more bulky and cost you would have to incur. All right. And then for the inverter design, we have to consider the battery design. And then at the end of the day, we have our final design once we have put in place all of these important parameters. So we design our charge controller, we design the battery, we design the inverter, we design the PV array. When designing the battery, we take into consideration the days of autonomy. When designing the PV array, we take into account the sun hours, the losses, and then the load demand. All right. How do we analyze our load? First of all, how do we analyze load? And how do we analyze days of autonomy? Those are the two things we want to pay attention to right now. How do we analyze our load? How do we analyze the days of autonomy? When analyzing your load, you have to take into account quantity. Okay, so load, your electric bulb in the house is load. The television you use in your house is load. The DVD players in your house is load. The refrigerator, the microwave oven that you use, the washing machine, the computers you use in your house, all the electrical appliances in your house, the iron, they are all types of load that draw energy, that places demand, on your utility for energy before they can be used. All right. So you have to ask yourself, what is the quantity of my load? When you're analyzing your load before designing your PV system, you have to carry out load analysis. So you want to ask yourself, what are the loads that I have, or what are the loads that I want to meet or that I want to supply with my PV system? All right. Once you know the load, you ask yourself, how long would I use this load on a daily basis? And then that would help you to know how long you will use it on a weekly, monthly, or annual basis. Then you want to ask yourself again, what is the power rating of each of these load? When you know the power rating of each of the load and you know the amount of time that you want to use the load, you can easily find the energy each of the loads would consume. So once you have done that, you want to ask yourself again, what will then be the total energy of all the loads put together if I'm going to use all of this load? Maybe 5 load, 10 load, 6 load, 7 load, whatever the number of loads are, you know the energy each of them will consume. And then you want to say, okay, in one day, what would be the energy requirement for all of these loads? If I'm going to meet the energy requirement of these loads per day, what would be the total requirement? Then you add everything together. And then again, you want to ask yourself, which of these loads are AC, which of these loads are DC? So I can know the amount of AC energy I need and then the amount of DC energy I need. All of these fall under, the load analysis. So to make that happen and easy, we're going to use a simple example to quickly, go through all of those so that you can easily crystallize the concept that we're talking about. Okay. So let's go. Here is a simple, a simple house. Let's say as a student, you have a very simple house here, and then in your house, you have probably 4, lights. You can see you have light here, and then you have 4 quantity. The quantity is 4, all right? The power for each one of them is 24 watts, and then these lights are DC, they consume DC energy, okay? So you have 24 watts per item. It simply means total power that these lights will draw will be 25 for 1 multiplied by 4, because we have 4 of them. That will be total power of 100. So you can see that your item would draw power of 100 watts DC, because they use DC. You probably want to ask yourself, if you're a student, you leave the house in the morning, you don't come back home until in the evening, and when you are home in the evening, you spend just 3 hours in the evening, to cook, to eat, to drink, to, play around a little bit. And then after 3 hours, you switch off your light again, and then you go to sleep. So in a full day, let's say that you used your light just 3 hours in a full day. If you use your light just 3 hours in a day, and you multiply power that is drawn by this light by the 3 hours, that will give us the total energy that is consumed by the lighting system. So 100 times 3 will give us 300 watt hours. All right, so this falls under the category of DC. We are assuming that the only appliance in the house that's using DC energy is the light bulb. So if that is the case, the total DC energy that you would need in your house is equal to 300 watt hours. So you keep that somewhere. And then you ask yourself again, what are the things that I have in the house that use AC energy? Since you are just a basic student, basically in the house, the only things you have is just your TV and then your computer, your desktop. And these are actually, they consume AC energy. So you have just one TV, you have one desktop, and then each one of them is 100 watts power. The TV draws 100 watts AC. The desktop draws 100 watt AC. All right, so total power drawn by the TV is going to be 100 multiplied by 1. So if you multiply 100 by 1, it gives you 100. If you multiply this 100 by 1 again here, it gives you 100. So if you add all of this together, it gives you total power here, total power drawn, total AC power that you need, okay? Then again, let's say you use your TV for 2 hours. When you come back home, by the time you're done cooking and all of those, you have just 2 hours left to, to watch TV. So you use your TV for 2 hours, okay? And then you use your desktop for just 1 hour before you eventually go to bed. If you use your TV for 2 hours, it simply means that if you multiply power by the time of use in hours, you are going to end up with watt hours if the power is in watt. All right, so 100 times 2 gives us 200 watt hours for your TV, and then for your desktop it gives us 100 times 1, because you're using your desktop for just 1 hour, so that gives you just 100 watt hours. So what you will find out here is that total power drawn by your AC appliances is 200. Total energy consumed by those AC appliances is 300 watt hours. All right, so now we know that we have total AC of 300 watt hours, total DC 300 watt hours. Total DC power is 100 watt DC. Total AC power is 200 watt AC. Total energy consumed, total DC energy consumed is 300 watt hours. Total AC energy consumed is 300 watt hours as calculated here. So you can see that we have an understanding of all of this. And since we are designing a standalone system, we want to know, okay, what happens if your PV is not generating? Okay, or what happens if it's in winter and we don't have enough sun to, for the PV to generate energy? So you want to incorporate a battery because you are using a standalone PV system. So when you incorporate a battery, how many days do you want your battery to work? How many days do you assume that it is possible that you don't have enough sun to be able to provide enough energy for your appliances? So let's say 2 days is going to be safe for you. So in 2 days, you believe that, at least sun will shine at least once or twice, and then your battery can be recharged again. So in 2 days, your battery can last for 2 days without being charged. Okay, so our days of autonomy is going to be equal to 2 in that case. So for your design, you could use days of autonomy to be 3 days. You could use days of autonomy to be 4 days. You could use days of autonomy to be 5 days. You could use anything for your days of autonomy. All right. Okay. Let's take it a step further. So we've talked about our load demand, right? And then we've been able to factor in the load demand. So we know the amount of energy we would need for our DC load. We know the amount of energy we would need for our AC load now. That falls under load analysis. Now, and we already know our days of autonomy. We dealt with that too. Now we will talk about losses. So we want to estimate the minimum power that the PV array is expected to deliver. How much power is the PV array expected to deliver? The minimum, so that we can use that to, factor that into our design. Let's try to find out how to fix that. This is what would happen. How much power are we expecting our PV array? And the way to do that is to first of all account for all the losses. And then once we have been able to account for all the losses, we'll know exactly what is left. Okay, that will be coming in. So let's pick that up from this angle. Where did we get this 745 watt hours from? I'm going to show you right now, because this is the amount that amount of energy we expect our PV to deliver. Okay. For example, we are dealing with AC, and then we are also dealing with DC. Okay. We are dealing with the battery, and then we are also dealing with inverters. Okay. The battery has an efficiency. The inverter also has an efficiency. So for the inverter, the efficiency, let's say 90% is 90% for this case. For the battery, let's say the efficiency is 85% for this particular case, as you can see here. You will first of all look for the energies that would make use, or the appliances that would make use of inverter, and then the appliances that would make use of the battery. First of all, when we are dealing with the AC load will deal with both the battery and the inverter. All right, because this is the AC load here, as you can see. So when the energy comes from the PV array, it goes to the battery, and then from the battery, if we are drawing energy from the battery, it passes through the standalone inverter before it is converted to AC energy. Okay, so the AC load would have to factor in the efficiency of the inverter and then the efficiency of the battery and the cables, all right, which is given as 85%. The AC load will factor that in. And then the DC load, as you can see, the DC load is not passing through the inverter at all. So the DC load is only going to take into account just the battery efficiency, because from the battery here, before the energy gets to the inverter, we are going to draw the DC load, and then we go this way. So for the DC load that is not connected to the inverter, we just write it here as 300 plus the AC load, total AC load that we calculated in the previous slide. So from the plus the total AC load, this total AC load, since AC load is connected to the inverter, it gives us 3 watt hours divided by 0.9 or multiplied by 1 over 0.9, all right, which is going to be the efficiency of the inverter. So this is accounting already for the inverter, and then this is just there, all right. So when we add both of them together, since both of them are going to be accounting, both the DC and the AC are going to be, account for the battery. So if we add them together, you divide it by the efficiency of the battery, which is 85%. And that is why you have these here. To make it easy for yourselves, you don't have to, memorize these or something. You can just say, okay, you can say, okay, your DC load is 300 watts. So you say you have 300 watts for your DC divided by 0.85. All right, for your DC, divided by 0.85, because that is only, going to connect to the battery. Okay, then plus for your AC load, it will be 300 watts, because we calculated 300 watt from our calculations, the example we are using for this calculation, divided by, you have the inverter, which is 0.9, because the AC load will pass through the inverter, 0.9. It will also pass through the battery, 0.85. So this is another method you can use to find that. So when you have these two together, you're going to get the total energy that your PV array is supposed to produce. All right. So if you punch your calculators, everything will give you 745. If you go through this particular route, everything would also be equal to 745 watt hours that we are expecting from the PV array. All right. So these two mean the same thing. These two, they mean the same thing, right? This place, they mean the same thing. Okay. If we are not making any mistakes, they should give us 745 watt hours. All right. So what you can see here is that your PV must produce 745 watt hours. Otherwise, you won't be able to meet your load requirement. If your PV doesn't produce up to that amount, you won't be able to meet your load, your total load requirement in the house. The reason we have done this is because we have accounted for the losses. All right, we have accounted for the inverter losses, and then the inverter losses, and then the battery and cabling losses. That is why we had to use their efficiencies here to make the calculation. Otherwise, we could have said the PV array should just produce 600 watt hours, because we have 300 watt hours for DC, 300 watt hours for AC. And then we can just come and say, look, let our PV array produce 600 watt hours, and those should be enough to meet our load requirement. But then if we are using a battery that has an efficiency of 85%, an inverter that has an efficiency of 90%, it simply means that along the line, you will lose some of this energy. So when you lose some of this energy, it means what will eventually get to your load would not be up to 600 watt hours anymore. So the losses that are going to occur along the line are the things that we accounted for by using the efficiencies of the battery bank and the inverter to calculate the amount of energy that we must supply that the PV array must deliver. And at the end of the day, we got 745 watt hours. If these 745 hours get to the battery and we remove losses on the battery from there, and also get to the inverter and we remove the losses of the inverter from 745, what we would eventually have delivered to our load would be exactly 600 watt hours. And this would have met our load requirement. This is very important for you guys, okay? Let's take it a step further. We've talked about the load demand. We've talked about the losses. We've accounted for the losses. We've talked about days of autonomy. Now we want to talk about the equivalent on hours. Depending on the location that you are in, all right, you want to find out the average equivalent on hours per day. In Cyprus, it's about 4.5 hours per day. There are times when it's as high as 7, 8, okay? And there are times when it is as low as 2, 3. When you take the average of what is going on, you could have equivalent on hours of about 4.5 usable sun hours for your PV as 4.5 hours per day. That's the approximation that we have here. And this is actually for the winter season, by the way. In summer, it's going to be higher than this. So when you are calculating or trying to carry out this design, it's better to design with the lowest value in mind so that you can cover all ends. So we have handled the load demand, we've handled the losses, we've handled the equivalence on hours. Now it's time for us to design our PV array. What should be the size of our module? That's the next question you want to ask right now. What should be the size of your PV system? What size of PV system should you install that will now produce 745 watt hours of energy? Okay, that's the next question that we want to deal with right away. So now we want to design a PV array now. We want to design our PV array. We want to know how many modules do we need? What should be the size of the PV array, the capacity of the PV array, all right? First of all, you want to know your panel specification. What is your module specification or your panel specification, okay? Because we are using a crystalline silicon module, you can call it a panel if you want. You can call this a module, you can call it a panel if you want. Okay, so what would be the specification? Let's assume that the specification of the PV module we want to use is this. We have the power output of 100 watt, and then we have the maximum power point voltage to be 16 volts. We have the maximum power point current to be 6.2 amperes. We have the open circuit voltage to be 20 volts, and then we have the short circuit current to be 7 amperes. Okay, it could be another module. If you are using another module, you know, the specification is going to be a bit different. Okay, so if we are using this particular specification, what you would find out is we're going to make our calculations like this. So what is the minimum watt we need for our array? What is the minimum watt we need for our array? Okay, so we know that total energy that we want our PV array to generate is 745 watt hours from our calculation. And then we also know that total sun we have per day is 4.5 hours a day. So if we want to know the amount of the peak power that we need for the entire system that we want to install, it should be 745 watt hours divided by 4.5 hours for that day. So if hours cancel hours, 745 over 4.5 will give us 165.6. Okay, so you have 165.6 watt. So the total amount of power that you need is 165.6 watt. And then again, you know, the kind of module you want to use, is about, you know, it has 100 watt peak. So it simply means that if you want to know the number of modules to use or number of panels that you can use for your system array, it should be number of panels will be equal to 165 watt, which is total power for all the entire array, divided by the peak power of one of the modules. If you do that, you're going to obtain 1.7. All right, so you're going to obtain 1.66, something like that. If you approximate that, it's about 1.7. So there is no way you can have 1.5 module. There is no way you can have one module and then cut another one into half or into, you know, 0.7. No. So what you do is you approximate this 1.7 to a whole number, and then this gives us 2. In order to ensure that you do not lose any energy, you have to use 2 modules. Okay, when you use 2 modules, then you want to ask yourself, should they be connected in parallel or should they be connected in series? If they're going to be connected in parallel, what should be the maximum current and what should be the maximum voltage? By the way, you have just 2 modules. Okay, so that question is very easy to answer. So these are the possible configurations that we can have. We have decided that total power output we need is 165.6 watt. We have also decided that total number of panels or modules we need will be 2, okay, to meet our load demand. We have that here. And then one of the connections that we can have, one of the possible configurations that we can have is to say that it is to use our maximum current, find our Imax. Imax is the maximum current possible that can flow through the array. So Imax would be equal to 7 times 2. Where is this 7 coming from? This 7 is a short circuit current. Okay, it's one of the parameters of the module that we have, the module that we are using. Okay, so it's going to be 7 times 2, and that gives us 14 amperes. This is the maximum current that we can experience. Again, what is the maximum voltage that we can have? All right, if we have a parallel connection, we're going to consider maximum current. If we want a series connection, we're going to consider the maximum voltage. All right, so for parallel connection, you know that the voltages are constant for parallel connection, and then the current varies. For series connection, you know the current is constant, and then the voltage varies. Okay, so that is why for series connection, we have to look for the maximum voltage, and then for parallel connection, we have to look for the maximum current. So for maximum voltage, it will be equal to the open circuit voltage, we have VOC when there is no current at all, multiplied by 2, because we are dealing with 2 modules, and that will give us about 40 volts. Okay, so with this particular scenario, you have an idea, you know, of the maximum current you can have and the maximum voltage you can have, you know, for 2 possible configurations that exist. So at this level, we want to now go ahead and design our charge controller. We have been able to design the load. We have an idea of the equivalence on hours. We have collected our data for equivalence on hours. We have data for load analysis. We have data for accounting for losses. We have data for the PV array design already. We just finished that. Now we want to talk about the charge controller. All right. The charge controller parameters would conform with the maximum parameters found in the different PV configurations that we have. All right. So we have to make sure the parameters of the charge controller conform to our PV configurations. Okay, so let's see how that plays out. For the charge controller that we want to use, we have to look at the specification and then try to make some calculations. So the maximum voltage for the charge controller, for example, if you are using this particular type of charge controller, the maximum voltage is 60, all right, 60 volts here. If you notice, the maximum voltage for our PV configuration is Vmax. So the charge controller voltage is greater than the Vmax. Again, maximum current is 10 amperes for this charge controller. You will see that this is lower than what we obtained, okay? The operational voltage of this charge controller, the nominal operating DC voltage, okay, it has to be the same as that of the battery bank, all right? So this is 12 volt or 24 volt. So we have to go for a charge controller of 24 volt. This has to be dictated, this has to be based on the rating of the battery bank, okay? So given a choice between series and parallel connection, series configuration is preferred to keep the current levels down, thereby minimizing the DC cable losses. Okay, so one of the reasons why you want a series connection is because you will reduce the current. In series connections, the current is constant. Okay, so you reduce the current that way when you connect the modules in series. So we choose this connection to reduce that. So if the panels are connected in series, what then happens? The maximum current doesn't support the parallel configuration because the current here is lower than the current that we have for the parallel configuration. So what you want to do here is that this MPPT charge controller supports the series configuration, because this will help us to keep the current as low as possible. We just go for series connection, because if we go for parallel connection, that means we're talking about 14 amperes here, which is more than the current of the charge controller. All right, so that's why we want to go for the parallel connection. This puts us in a safer mode, and that would also reduce the current as much as possible. So we've talked about the equivalent on hours and every other thing. The next thing we want to talk about is the battery, the design of the battery. The battery size is greatly affected by the days of autonomy. Okay, so the days of autonomous operation expected from the system would affect the battery size. Thinking about that, we can then go ahead and say that, okay, the battery specification we want to use is this. The depth of discharge of the battery is 60%. So the battery voltage is 12 volts, and then the battery capacity is 21 ampere hours. Just like, I've explained most of these terms to you just before we got to this point. So the question is, how many batteries of the given specification should be there in the battery bank? How should they be interconnected? We'll find that out right away. All right. Now, minimum battery capacity will therefore be equal to 745 watt hour. This is the total amount of energy that we expect our PV to deliver, divided by the depth of discharge of the battery multiplied by the operational voltage of the system. All right. The operational voltage of the system, like we mentioned the other time, is 24 volts. Multiplied by the depth of discharge of the battery given from this particular specification. If you do that, multiply that by 2. This 2 represents your days of autonomy. So once you do that, you would obtain 103.5 ampere hours. So the lower the battery depth of discharge, the higher the battery bank capacity requirement. This is very important. The lower the battery depth of discharge, the higher the battery bank capacity requirement. When the DOD is high, it means the battery can be discharged more. For example, a 60% DOD simply means that you can only discharge 60% of that battery. All right. So when the depth of discharge is just 50, then probably you will need more batteries to be able to discharge up to the amount of energy that you need. But then when the depth of discharge is about 70 or 80, it simply means that you can discharge more energy from that particular battery. So the higher the battery depth of discharge, the more the battery can be discharged, all right? And therefore, the lower the battery bank capacity required. So that simply means that one battery can actually serve all your need if the depth of discharge is high, all right? And if the depth of discharge is low, you may need more batteries. You will need lower number of batteries if the depth of discharge is high. You will need higher number of batteries if the depth of discharge is low. Please pay attention to that. So total capacity of the battery that is needed is 103.5 ampere hours. So we want to find out now the number of batteries that can be connected in series and the number of batteries that can be connected in parallel. All right. So let's take quickly do that. So minimum battery capacity is 103.5 ampere hours. We fixed that already. Then number of batteries in series will be equal to 24 volts divided by 12 volt. Number of batteries in series will be equal to 24 volt divided by 12 volt. 24 volt represents the system voltage, while 12 volt represents the battery voltage. All right, 24 volt represents the system voltage, 12 volt represents the battery voltage, and we want the battery bank to have the same voltage as the entire system. So number of batteries connected in series will now be equal to 24 volts divided by 12 volts. That will give us 2 batteries. So with 2 batteries connected in series, we can have 24 volts that commensurates with the voltage of the system. The total capacity of the battery bank is 103.5 ampere hours, and then the capacity of one single battery is going to be 21 ampere hours. You have 4.93 when you divide 103.5 ampere hours by 21 ampere hours. You have 4.93. So since you cannot have 4 batteries and a half, you can't have 4 batteries and 0.9 batteries. No, you either have 1 battery or 2 batteries or 3 batteries or 4 batteries or 5 batteries and so on. So you want to convert whatever value obtained here to a whole number. So here, approximating this gives us 5 batteries. So if we are going to have 5 batteries in series, and if we are going to have 2 batteries in series, 5 batteries in parallel, it means the total number of batteries that will be needed will be 2 times 5, and that will give us 10 batteries altogether. So 10 batteries in our battery bank is what is needed to meet up with the requirement of the PV system that we are designing. All right, so we have been able to deal with every other thing. Now we want to talk about the inverter design. Based on the efficiency of the inverter, the power rating of the inverter needs to be calculated. So how do we find the power rating of the inverter? So let's say that this is the inverter we want to use. So and these are the specifications of the inverter that we have chosen to use. So we have the efficiency of the inverter as calculated. We know the efficiency is 90% already. We talked about that in our calculations. And then the operational voltage of the inverter, we mentioned that too. It's about 24 volts because it has to be, everything has to be synchronous in the system, especially when it comes to operating voltage. So what should be the minimum power, the minimum nominal power rating of this inverter? The minimum nominal power rating of the inverter will be equal to 200 watts divided by 0.9. The inverter will be rated in terms of power, not in terms of energy. So don't forget that the total power that we need, total power demand that we need for AC. Okay, for the DC, we don't need inverter at all. Only the light is using DC. If you can remember our calculation, only the light is using DC and it's 100 watts. So the TV and the desktop are the only AC loads that we have. And the total power rating for those two is 200 watts, okay? So that 200 watts divided by the efficiency of the inverter will give us 222 watts. And that simply means the power of our inverter has to be at least 222.2 watts. This is the end of this session, and I hope you have enjoyed the teaching. Please remember to subscribe to this channel. Give this video a thumbs up if you like it, and I'd really love to read what you think about this lesson, photovoltaic systems and off-grid power systems in general. See you at the next lesson.